All right, example 3 is a word problem. So let's make sure you understand what's happening here. So the Russell family is driving 1,000 miles to the beach for vacation. They're driving at an average rate of 60 miles per hour. Okay, write an equation that represents the distance remaining, right, and the time in hours that they've been driving. So I have two things that I'm looking for. I have my D which is distance remaining. First thing you always want to do is identify your variables. Okay, and then I have H, which is the hours. Right? Now when we graph, we need to identify which one's your dependent variable, which one's your independent variable. Right? The amount of time you drive is independent. It's just you get in the car and you drive. And depending upon how long you've been doing that, you will be closer to your destination. So the time, the distance that's left is going to be dependent upon how long you've been driving. Okay? So H is your independent variable and D is your dependent variable. When you go to graph this on the coordinate plane with X's and Y's, that's the equivalent of using H as your X and D as your Y. Okay? So this, D, should be your vertical axis, right? Your Y-axis. And the X should be, with the H, should be your X, or your horizontal axis, your X-axis. All right? So, now that we know our variables, we need to put our equation together. All right? So, if we think slope-intercept form, we want something to equal D. So, D equals. D is the distance left. Well, the distance left has to start somewhere. So, how far have you traveled, or how far do you have left to go if you haven't been driving yet, if you haven't even started the car yet, right? So how long is the total trip? They're driving 1,000 miles to the beach for vacation. They started with a distance left to go of 1,000 miles. That's your initial value, okay? And then as they drive per hour, every hour they go 60 miles. So every hour they're 60 miles closer to their destination. So they're losing that distance, right? So that'd be subtracted. So minus 60 per hour, right? So there you go. There's your equation. Okay, write an equation that represents the distance remaining in miles and the time and hours they've been driving until they reach the beach. They plan on stopping 4 times during their trip. Draw a graph to represent all the possible distances and times that they can stop on their drive. So, how are we going to show that? First off, let's talk about a few things before I go over my graph paper and graph this. 1, does it make sense to graph this in 4 quadrants? Or would you want to only graph it in the first quadrant? Okay? Hoping that you're thinking in your head, we need to graph the first quadrant. The reason being is you can't travel negative hours, and you can't have a negative distance limit. Once you hit 0, you're there. Okay? So we only need first quadrant here, which means, and since my numbers are kind of bigger, I'm going to go ahead and make a bigger sort of graph. All right? So, next we're going to go on and we're going to graph this. All right, so first thing I'm going to do is write my equation down. D equals 1,000 minus 60H. And just for understanding purposes, I can swap this around and swap my variables for X and Y to help me kind of graph it. Okay? So if that helps you to do that, feel free to make sure you do it. Yeah, here we go. Let's see. Now, be smart about this thing, okay? I know where I started, so what I really want to do is try and count by something that makes a lot of sense graphically. All right, so we're going to start with 1,000 up here, okay? And it would make sense, since I'm losing 60, right, to make my lines nice and neat. What if we counted down by 60? So 940, okay? And then 880. Now, I don't know when we're going to get there, and we may not have a big enough graph, but we should get a pretty good idea. All right, so 820, if we were to keep this going, that'd be 760, and then 700, and then, all right, I'm just going to keep this pattern going for a little while. I was close. That means that right below, right about here, my x-axis will be, and we'll, you know, it's not perfect, but it'll definitely give us a pretty good idea. Okay, in case you're wondering why I went a little above, right? Let's think about it. So this is 40. I wouldn't have to go all the way to 60, right? The next line would actually be negative 20. We don't really need to go to negative 20, right? We just need to go to 0. So I drew my x-axis at 0. Just a little bit of puzzle line on my grid paper. All right, so I know my intercept's up here, and it's negative 60 over 1. Now, the reason I did my 60s, or the reason I did 60 by 1, again, this would be 1 hour, 2 hours, 3 hours, 4 hours, 5, 6, and so on, right? Okay, so again, this is the hours to travel, and this is the distance left. Distance left for the trip. Okay, so because each line down is 60, and each step across is 1 hour, it's really a 1 over 1 in terms of the way my graph looks, which means even though it's a negative 60 for slope, it doesn't mean I go down 60 and right 1. It means I go down 1 line because that's 60 units and right 1. Down 1, right 1. It allows me to graph a very nice, neat, linear graph. Okay, so in terms of what we're doing here, 1 hour, 2 hours, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 hours. Okay, and then somewhere between that, it would actually be like 16 hours and 40 minutes, right? They would actually get to their destination. Okay, so it's a pretty long trip for them. So there's the graph of all the nice, neat whole number answers. After 1 hour, they'll have 940 miles left. After 2 hours, they'll have 880 miles left, so on and so forth. Okay, are those the only possible solutions? Right? What if they've only traveled for 30 minutes? Right, half of an hour. Then they would be halfway through here. They'd have 970 miles left. What if they traveled an hour and a half? They'd be halfway between these two numbers, which would mean they would have 910 miles left. So there are a bunch of solutions that are actually in between all of these dots, all of these discrete dots. So we do indeed need to connect our line as best you can to represent all of the possible solutions. Now, since this was an equation and had an equal sign, there's no shading or anything like that. But these right here are all the possible solutions. Now, would there be an infinite number of solutions here? Technically, yes. Reality, probably not so much. Because you're going to count by either seconds or minutes or hours. So you're going to have a limited kind of window there. But technically, there are an infinite number of answers even within this little range that you have here. There's not an infinite number of answers that make good sense, but there are actually an infinite number of answers. Okay, so there's your example for that.